The treatment of numbers called digital roots is a well-known and fairly simple process. It involves taking any whole number and treating it as a string of digits to be repeatedly added until only one digit remains, a number between 1 and 9. When applied to the primes, I have found a sort of pattern, but it is not so rare as I once thought. This is because of an important rule in digital roots. Firstly, though, an introduction. Digital roots are produced by repeated rounds of addition on any whole number. Regardless of how you break up a number, the addition process always produces the same digital root. Even with larger numbers, as long as you recognize that every whole number has a digital root, the result isn't that surprising. When applied to the prime numbers, there is also an important characteristic to note. All numbers with the digital roots of 3, 6, or 9 are divisible by 3. This is important to the primes because it automatically excludes a huge number of potential candidates. That is to say, 1/3 of all numbers cannot be primes because their digital root is 3, 6, or 9. This number has a digital root of 3 and is also divisible by 3. This number has a digital root of 9 and is also divisible by 3. They are all guaranteed to be divisible by 3 and are therefore disqualified from being prime numbers. What is unusual is that numbers with the digital root of 2, 4, 5, 7, and 8 are not necessarily divisible by those numbers. That is to say, this number has a digital root of 5, but it is not divisible by 5. It is also not divisible by 3, 6, 7, or 9. It is divisible by 4 and 8, and of course 2, because it's even. This is just to point out that, apart from even numbers being divisible by 2, and all divisible by 1, a whole number is not always divisible by its digital root, unless it has the digital root of 3. This number has a digital root of 8, but it is not divisible by 8. It is also not divisible by 3, 5, 6, 7, or 9. It is divisible by 4 and, of course, 2, because it's even. Even numbers with the digital root of 2, like 1721, are not necessarily divisible by 2. This becomes especially clear in the primes, many of which have a digital root of 2, 4, and 8. This is just to point out that, when it comes to digital roots, divisibility of a number by its digital root can be quite unclear. The rule of divisibility by 3, if a number's digital root is 3, 6, or 9, is one of the few rules that can be reliably followed. It should also be noted, again, that divisibility by 1 is a given, and that many primes have a digital root of 1. This is the first 300 primes in order, arranged in 3 blocks of 100 each. So now on to the digital roots of the first 300 primes. We know that the primes will never have a digital root of 3, 6, or 9, and here I have to point out that the first appearance of 3 will be treated as an exception. It must be claimed that there are no more appearances of digital root 3 ever again in the primes, and that if there were, something totally unforeseen has occurred. Just use an online digital root calculator and input some very large primes. Three should never again appear after the prime 3 itself. Likewise for 6 and 9, although these don't even appear once as primes, and for good reason. At last we're left with the digits 1, 2, 4, 5, 7, and 8, which will always be the digital roots of the primes. Picking out patterns from here is not the best idea, because it's exactly the same probability as rolling a 6-sided dice 300 times. So if you roll 3 threes in a row, sorry, that's not a pattern. Not one worth complaining to your dice maker about, at least. In fact, you need to roll at least 15 identical rolls in a row on a dice to be statistically significant. This is because a 1 in 6 chance is very likely to produce many repetitions. The pattern I highlight here in these digital roots is also a 1 in 6 chance, so I've got a lot to prove with just 300 instances. But as far as I can tell, this could be a worthwhile pattern to follow, especially if more repetitions occur and if longer strings of repetitions occur. I haven't done the next 600 digital roots, but I might in my next video. Nevertheless, depending on each pattern and its significance in light of more serious prime number research, it will be interesting to see what adds up. Thanks for watching.